Well, good afternoon, everyone. My name is Andy Howard. I'm an applications engineer with the Keysight EDA software organization. And I support the field primarily in the US, but also around the world. And I've created a lot of examples that are related to power amplifier simulation over the years. Before I get started, I'm just curious, how many of you are power amplifier designers? Only one, two, only two people. Everyone else is not.
I've designed in the past, but
Not currently, okay. Anybody who's an ADS user? One, two, what, a handful of you? Okay, but not power amplifier design. Okay, all right, well, this will, some of it will be directly, well, I guess for a lot of you, it won't be directly applicable, but I think it's still interesting material. Let me just give you a little bit of background about it. This presentation is about using measured load pull data, reading and measured load pull data, and what you can do with it in ADS. Yeah, so that's, in power amplifier designers often need to read in measured load pull data and use it. And that's primarily what this is about. So it's kind of a specific topic, but some of the things that I'm going to talk about are, I think, more generally applicable, like creating artificial neural network models is something that can be done with a lot of different types of data. And I think that will be something that's more widely of interest to designers, and that's not specifically limited to power amplifier designers. Okay. So this is the agenda. I'm going to first give an example of where we're going. I'll talk about RF power amplifier design challenges. Some of the issues with working with measured load pull data, modeling with artificial neural networks, and then I'll talk about some specific things just using the artificial neural networks within ADS and what you can do with them and what benefits they provide. Okay. This is, oh, come on. Come on. This is an end result. Power amplifier designers may want to read in measured load pull data and use it to optimize a matching network. You have if you're designing a power amplifier, ideally you have a nonlinear transistor model that you can use in the design process. But sometimes those models aren't available and all you have is measured load pull data. And you can, using this technique or the techniques that I'm going to show, you can read that data into ADS and then use it to continue the design process or use it in a design flow. And by that I mean design an impedance matching network so that you can get the performance from the transistor that you want or make trade-offs. Okay, and this is a very simple example. It's just meant to illustrate the concept, but this is an optimization result, and it shows performances such as gain and power, or gain and efficiency versus output power, an optimized gain and efficiency versus frequency. This is optimized power versus frequency as well. And this uses data from 4 different measured load pull data files. and shows the performances versus frequency as well as the matching networks parameter values. So this is a really simple example. I think it's useful to start simple, but this is kind of the end result. You could use this as a starting point for designing a more realistic impedance matching network. Okay, I'm going to talk about some of the design challenges that RF power amplifiers face. As an RF power amplifier designer, you have to choose a transistor to use, and you need to know what sort of performance could be achieved from a particular device. And you can get that from a data sheet or from reading in measured load pull data and working with it within ADS, examining it. If there is a nonlinear model available, that's useful. You can do a lot more in simulation than you can if you just have to work with measured data, but there may not be a nonlinear model available, so or it may not be sufficiently accurate. So in that case, you may be limited to working with measured load pull data. So you have to make trade-offs. How do you choose the impedances to present to the device? How do you use the measured data to optimize your impedance matching network? This presentation assumes that you must use measured load pull data. If you have a nonlinear model, like I said, there are way more things you can do, and I have a ton of examples that show different capabilities if you have a nonlinear device model. But we don't have one. We're making the assumption that we do not have that available in this presentation. This is specifically for working with measured load pull data. One thing about measured load pull data is that there's a lot of different file formats available. Different measurement system vendors write out data in different file formats, and the way they write out data is all over the map. They have different variable names, different ways of formatting the data. They sweep lots of different parameters. It's very flexible, tends to be complicated data. It's irregular. What's in the files varies a lot. Sometimes there's usually power gain and efficiency, but sometimes there's phase, there are input impedances, sometimes there are A and B waves. Sometimes you see error vector magnitude, adjacent channel power ratio data, how the load is swept. Sometimes it's not even swept, sometimes it's the source impedance that's swept. There's just a wide variety of data, and working with it in being able to read it in and then use it is complex. It's often irregular, and it's almost always irregular. It's often the case that the data has invalid points. And if you're going to use this data directly in an optimization, you need to be able to interpolate it. That's a big deal, being able to interpolate. And that's one of the key contributions of using artificial neural networks.
I'm sorry, what is the y-axis here?
The y-axis is the power delivered to the load.
Oh.
Yeah. Yeah, so each one of these lines is a different load impedance, and the power was swept in the measurement. And for this particular measurement point, the data is irregular for whatever reason.
The units are dBm or?
dBm, yes, in this case. The data can be, well, it's typically unformatted, raw measurements.
And the data, is it measured with the load matching or without matching?
it's usually measured without matching. The load is tuned. So you typically have an unmatched transistor, and the load is tuned, and we're trying to see how does the performance from the transistor vary as we tune the load. And then once you see what the optimal load is, or how the performance varies, then you can say, okay, well, I need to come up with a matching network that generates a particular load, possibly across frequency, and then you have to come up with a matching network that does that.
The load is not 50 ohms.
It's typically not 50 ohms. Load pull means varying the load over some region of the Smith chart. Yeah. So.
I see. And you said tuned load.
Right, that's right, yeah. One of the things you want to do, probably the first thing you want to do in ADS with measured load pull data, is bring it in and plot it so that you can just look at it and see where the contours are. These are contours of power and efficiency, and but you could have other things like bias current or error vector magnitude or adjacent channel power ratio, gain compression. Then you want to take this data. I mean, some people are satisfied with this, but you can also take the data and use it to optimize matching networks. And ultimately, people would like to say, okay, well, I have this measured load pull data. I want to bring it into ADS and simulate it as a nonlinear model. Why can't I just do that? Why can't I just read it in and do nonlinear simulations with it? And that's tricky, but we're working on that, and I'll show an example of that at the end. Okay, so the next topic is working with measured load pull data, and almost everybody wants to do this. Like I mentioned, the first thing is just bring the data into ADS and plot it, plot the contours so that you can look at it, and then determine what are the optimal impedances, what performance could be achieved, what are the optimal impedances to present to the transistor, what trade-offs might be necessary. This is a relatively new tool that we've introduced in ADS 2024, and it's an add-on, but it's a graphical user interface for bringing in measured load pull data, and it's based on Python. And when you have this added or installed, it's an add-on to ADS 2024. But when you have it, you launch it from the ADS main window here. Or actually, this is a schematic window. No, it's I think it's from a schematic window. You bring up this user interface, and you specify the file or files that you want to read, and sometimes the files are they have data at one frequency. Sometimes they have data at multiple frequencies. Sometimes the files have, like you might have 4 files or 5 files or several of a single device that's measured at different frequencies. So you can specify those and read them in. And this is an example of relatively clean data. There aren't any irregularities in the data at one input frequency. That's the source frequency. You can specify different frequencies, and the data will update here. So this is just a way to look at the data and see whether or not it looks valid. You're able to specify points that look noisy or invalid and exclude those from the subsequent post-processing of the data and reading into ADS. So this is specifying multiple measured load pool files. These were obtained from the Corvo website. These are measurements of a particular Corvo device at multiple different frequencies. And this shows the data at one of the frequencies after reading it in. And this shows contours of the measured load pool data. I think this is for transducer power gain. But you can look at other responses as well. This is not meant to be a replacement for looking at measured data on or using the ADS data display, but it's a way to quickly examine the data and see whether it looks valid or not, or whether there are any points that should be excluded. And this looks clean. I'm not seeing any problems with it, so there's no reason to exclude points from it. But sometimes you have data that looks like this, and this could potentially cause problems, maybe not, but if you find data, I mean, you can step through the different load points and look for irregular data and then exclude it from the subsequent post-processing or from the data sets that are written out or the artificial neural networks that are created.
Excuse me, do you have a block diagram for the test setup for this load
No.
measurement setup?
No.
I'm wondering how you create this file. What is the format of this file if I want to create a bench setup?
Yeah, no, I'm not talking about that here. That's a completely different topic. That's like an entire industry. It's a good point, but it's not. That's not what I'm talking about. It's you'd go to a vendor like Maori or Focus or CST or IVCAD. There are these large complex test systems that are used for running load pool measurements. And
these are standard file formats for this measurement?
They are standard file formats, yes. I mean, standard meaning each vendor, each load pool vendor has their own format. So there's not really a standard.
Okay.
You
support most of the popular formats?
Yes. Our intent is to support most of the main format. So here, this shows the file formats that we support currently, and these are from different vendors. And one of the things that we've tried to do is, because measured load pool data, file formats, variable names, whether the fundamental is the 0th index or the first index. I mean, it's just all over the map, and there's no standardization in the industry. So we have worked on a method of reading in different file formats and writing it into one kind of standardized file, an ADS data set that makes it easier to plot things and analyze the data. So that's hard to do. So I wouldn't say that we're perfect, but that's what we've been working towards. Okay, so this is an example of once you've read in the data or you've opened a file in the graphical user interface, and you've looked at it and you're happy with it, maybe you've excluded some points, you can then say file write ADS data set. That writes out a data set, and then you can plot it in ADS in the ADS data display. And this is I mean, there are many different ways to plot data, but this is one method, and this is specifically for analyzing measured load pool data for Doherty Power Amplifier design. And that's a specific type of power amplifier. You don't have to use this format. You can come up with your own format. And this is a very flexible tool. But that's specifically what this is for. Yes?
Just one quick question. Does the GUI allow interpolation within the data sets?
The GUI does not allow interpolation between the data sets. No, it does not. However, the resulting ANN, the artificial neural network that you can create from the measured load pool data files would allow interpolation. Yeah. Okay, so this is a Doherty Power Amplifier block diagram. This is a simple block diagram. And what I showed on the previous slide is a method of determining what impedances to present to the main transistor amplifier in that block diagram. And this is, or in this block diagram. So the load at the output of this matching network changes depending upon whether the peaking amplifier is on or off. So this impedance needs to change depending upon the input power level. If the input power level is low, then the main amplifier is operating at high efficiency. You want it operating at high efficiency. And as the input power increases, the peaking amplifier turns on, and you want the main amplifier to operate at a higher power level. So the loading it sees changes as the peaking amplifier turns on. So the load presented here is different depending on the input power level. Okay, so this is a plot of to help you determine what impedances to present to that main amplifier, and you choose a specific output power for the what's called the Z-mod impedance, where the peaking amplifier is about to turn on or is just barely on. And then this is where both devices, both the main and the peaking amplifier are on, and the main amplifier is now in a higher level of compression. But on this plot, or this data display is meant to help you determine a Z-mod impedance as well as a Z-opt impedance. The Z-mod impedance is found from this plot of the contours. And we typically would choose, although you can choose something different if you want, but we choose a gain compression level for the Z-mod impedance. In this case, it's 1 dB gain compression. This automatically finds the load on the 1 dB gain compression line that's closest to the maximum power added efficiency load. And then there's there's an X here, which you can't see very well, but there's an X here. And then this draws a VSWR circle centered on that impedance. And this impedance, this X, is the point on that circle that's closest to the maximum power load at this 3 dB gain compression point. And then these are the corresponding Z-mod impedances, and these are the Z-opt, the Z-mod impedance and the corresponding data for that load impedance, and the Z-opt impedance and corresponding data. So what you would do is based on these results, these are the target impedances that you would be using when optimizing an impedance matching network. Okay. So basically, the when the input signal is low, the peaking amplifier is off, and you want this impedance to be Z mod. When this is high, when the input signal is high, the peaking amplifier is on. The main amplifier, you want that to supply a lot of power or more power to the power combining network. And for that to happen, you want this to be Z opt. So the impedance seen by the main amplifier transistor changes depending upon the input power. And that's what this is meant to help you understand, just to see what those impedances are. Okay, so I'm going to talk about modeling data with artificial neural networks. So what I've shown so far is just reading in the data and then plotting it in ADS. Once you've done that, some people are satisfied with it, that's good enough. And you certainly don't have to be designing a Doherty power amplifier. You can just read it in, and you can read in the data, look at contours in ADS, plot the data, and kind of get an understanding of what performance could be achieved by a particular transistor and possibly across frequency. So I think that by itself is useful. That does not require artificial neural networks. I'm now going to talk about modeling the measured load pull data using artificial neural networks. Okay, well, why? What's the benefit of an artificial neural network? Why should we do this? Okay, so this is an example of measured load pull data. And it's not in a regular grid. It's kind of in a cloud, which is typically the case. Each one of these traces is a different measured load. And when you're optimizing, so we want to take this data and we want to optimize an impedance matching network based on this data. When you do an optimization, you have a candidate matching network, and what happens is the optimizer picks parameter values in the matching network, runs a simulation, and you get load reflection coefficients that are generated. So you get an impedance value. So this X would be, for example, the result of one optimization trial. And in order to evaluate whether that X is good or not, we need to be able to interpolate the data in the measured data file. And we need to be able to interpolate it efficiently. And we also need to be able to, this is the measured data, this is gain, but there's efficiency, there could be DC power consumption, there could be bias current, there could be other parameters that are of interest. But you may need to optimize performance at a specific level of gain compression, say 3 dB gain compression, or at a specific output power. Like maybe we want to optimize performance at a specific output power. So you have to be able to interpolate this data. And that's not easy to do typically. If somebody just gives you this irregular, poorly formatted measured load pull data, now you have to figure out, okay, well, how do I interpolate it? The ANN, the artificial neural network, takes your measured data and the parameters, the input parameters, and allows you to, or allows efficient and accurate interpolation to be done. That's the big advantage of ANNs, in my opinion. Other people may have other opinions, but that's what I think the main benefit of ANNs is, at least for this application. But when you're generating an ANN, well, previously, we're going back to this measured load pull data utility. Previously, we read in data, we wrote out a data set. So this is a different option here. under tools, build ANN equation model, we specify the data to include, these are going to be the outputs from the ANN. Power, the power delivered to the load, the transducer power gain, drain efficiency, power added efficiency. These are typically performances of that are in the measured load pool data file. It could be something else. It could be like air vector magnitude. It just depends on what was measured. It could be adjacent channel power ratio. But you specify the data, the outputs from the ANN model. And you can also, what we're doing is we're providing information to the ANN model generator. And ADS now has the ability to generate ANNs. You can give it data and the outputs that you want, and then and it'll generate an ANN for you. And we're basically specifying that information here. This step is this will automatically generate a schematic that can be used to validate the resulting ANN model, which is quite useful. That's an option. You don't have to do this, but it's highly recommended because otherwise you don't know how accurate your ANN model is. This is a simple ANN structure. I'm not an expert on ANNs. And I'm not going to explain ANNs to you because I'm not an expert at it. And you don't need to be an expert at it either to use this tool. But just to give you a little bit of background information.
So basically it's finding an optimal load based on your load pool data?
No. You mean an ANN or?
Yeah.
No, an ANN, an artificial neural network is a way of modeling your load pool data. It's an equation-based model. You have all this data. You have a bunch of measured load pool data. The measured data is things like output power, efficiency, gain, maybe bias current. Various things have been measured. The things that have been swept are the load, the load tuner impedance, the input power, and possibly the frequency. So I have this irregular collection of data that's based on this irregular sweep of a bunch of parameters. And I want to be able to take all this and use it in an optimization. And I can't do that because I have to be able to interpolate the data. I don't know how to do that. So the ANN is a model of the measured load pool data, and that enables me to interpolate it very accurately and very efficiently in an ADS optimization.
So you can have a test bench in which you have this model.
Yes.
You can run your simulations and verify.
Yes. Yeah.
And
And that's what I'm going to show. But this part, before you do that, you have to create the ANN model. And that's what this is an ANN model. You have to specify what the inputs are, the variables, and these would be things like the reflection coefficient, the real and imaginary part of the reflection coefficient, the input power, and the frequency if you have data over frequency.
Is it part of the ADS core or is it extra thing?
I think you have to have a harmonic balance license. I think it pulls a harmonic balance license to use it. Yeah. Then the outputs could be things like, would be the data that's in the file, things like the power delivered to the load, the gain, the power added efficiency. You can have multiple outputs. And the ANN model generation technique, what it's doing is it's trying to come up with these weights and these W and V values, which are weights that are applied in this network, so that you have a model that agrees with the original input data. Okay. And if you are knowledgeable about ANNs, you can choose different ANN settings and specify different parameters, number of training iterations, things like that, number of neurons per layer. I haven't had to do any of this yet, but I haven't worked with that many measured load pull data files, so I think it's probably going to be okay most of the time to just use the default values, but I'm not convinced of that. You know, it may be that there will be cases where you need to adjust the ANN settings, and but that's available. You can do that. The user interface does allow you to do that.
How do you verify your model generated is accurate?
That's this step right here. This is here. This step here, if you select this, it'll automatically generate a schematic which will simulate the ANN model for you using the same inputs that were used when you generated the model. And then it'll do a comparison between the measured data and what the ANN thinks should be the outputs. And those should align pretty well. And that's this. This was generated automatically. This is an ANN verification schematic, generated automatically. It runs a batch simulation, which is a type of parameter sweep within ADS, and it sweeps the same inputs that were used to generate the ANN model. And these inputs are the real part of the load reflection coefficient, the imaginary part of the load reflection coefficient, the input power, and the source frequency. And what's included here just depends on what data you have available. And the way this works is this is the ANN model, and it senses the load, which is swept based on these set gamma real and set gamma imaged values, senses the load, and the source power is also swept, and the source frequency is swept, and based on those, the load and these power and frequency values, it outputs the data, the gain, the power, the efficiency. And then it automatically creates a plot for comparing the data. And these are pretty much very close to each other. So that's an indication that the ANN model is working well. The x-axis is a different combination of the input parameters. Okay, so just to repeat, this particular ANN model is not like a transistor model. It's more like a lookup table. It senses the load reflection coefficient. This is your candidate impedance matching network that you're trying to optimize. It just senses the load reflection coefficient and also senses the input power and possibly the input frequency if that's a swept parameter as well. Then based on these inputs and the load, it outputs, it feeds that data into an equation and outputs things like the power, the gain, and the efficiency. And those outputs can then be put into goal expressions in the optimization. Then the ANN model is implemented using a netlist include component. And this is a standard component in ADS that allows you to read in a netlist fragment, and that's what this is. So this is a piece of text that has the ANN equations. Okay, this is a simple example of optimizing an impedance matching network. This is an optimization setup in ADS, but we have several different goals, one for the power delivered to the load, one for the power added efficiency, and one for the transducer power gain. And we have target values that we're trying to hit. And then we're also going to run this simulation across a range of frequencies because the ANN, the original measured data, had data in this frequency range. Although these could be, you could optimize in between these points as well. So that's not absolutely a requirement. You could optimize over a limited range instead if you prefer. This shows the optimization results. I showed these at the start of the presentation. Gain versus frequency, efficiency versus frequency, and power versus frequency, as well as the optimized parameter values. Okay, I was going to show a more complex Doherty optimization example. And let me just bring that up. Okay, let's see. Escape. There. Okay. And by the way, this example workspace is available to anybody who wants it. It's downloadable from our Knowledge Center, but we can make it available too. Okay, this is an optimization setup. I have one matching network. It's actually the same matching network. And I have two different conditions, two different external loads here. One's 50 ohms and the other's 25 ohms. The upper one is for optimizing the Z-mod condition, and the lower one is for optimizing the Z-opt condition. And if we go back to the, where is it? Okay, if we go back to the Doherty configuration. Oh, this one, okay. I'm basically trying to optimize this matching network under the two different load conditions. The load impedance seen to the right of the matching network is different depending upon whether the peaking amplifier is on or off. So when it's off, we see Z-mod here, and when it's on, we see Z-opt, a different impedance, a different target impedance here. So those are the two conditions, 50 ohms and 25 ohms, although these could be different values, certainly. Then these are elements that could be either an inductor or a capacitor, and they can change on the fly during the optimization. So this gives us a little bit more flexibility in terms of matching network configuration. And I'm specifying target impedances. We'd like to hit these target impedance values. These are from looking at a previous ADS data display at different frequencies. And then I'm also including things like the power gain and efficiency at the Z-mod loading condition, and the power and power added efficiency and gain at the XDB gain compression point. And we're optimizing across frequency as well, because we have measured data. The ANN model, well, the measured data was across frequency, so that's available in the ANN model too. And so basically what happens is at each optimization iteration, we get a Z-mod impedance and a Z-opt impedance. And based on those values, the ANN model senses those impedances, interpolates the data, and also does an optimization of the source power. Well, in this case, it would be the source power for the Z-opt condition. The source power for the Z-mod condition is actually optimized. This source power is optimized during the optimization. And the ANN model outputs data, transducer power gain, power added efficiency, output power, and that's used in the interpolation equations and then used in the functions as well to try to determine, to try to drive the error function to zero, or basically to meet the objectives that we've entered in the different goals. And as I said, that this is something that is done over frequency as well. So it's a complex optimization. We have two impedances, two load impedance conditions. We have multiple parameters in the matching networks that we're trying to optimize, and we're also trying to optimize across frequency, and we have multiple goals. So this is quite a complex optimization. But it doesn't take that long to run. It's probably, I think it's like 5 to 10 minutes to run, and the output is this. Okay, so this shows contours at the 3 different frequencies. The X's are the target values. That's Z-opt at the lowest frequency. These dots are what the matching network achieved. So it's not exactly on top of the desired target impedances, but it's close. And then this shows the results as a function of frequency for power, gain, and power added efficiency. Then these are the resulting optimized variables. The values that are, in this case, less than 100p are capacitors, and if it's greater than 100p, then they're inductors. So X2 is an inductor, X3 is a capacitor, X4 is a capacitor, X5 is an inductor, and so on. Okay. Let me go back to the presentation. Let's see if I can find it here. Okay. So the last thing that I wanted to do, I realize I'm running out of time. The last thing is you can generate a nonlinear ANN model. What I showed before was like a lookup table ANN model, but you can generate a nonlinear model if the data has power and phase, and if there's a bias current data as well, then you can use it to model efficiency. And this is a method of verifying the nonlinear model. It's the same as before with the kind of lookup table version of the model. And this shows that we have good agreement. The error is fairly small across power, gain, and efficiency. And this was a test of extrapolation. So this is a different type of model. It's a nonlinear model, and it senses the load that you present to it, that it sees, and it outputs a voltage and a current such that the correct power is delivered into the load. Whereas the other one does, the other type of model that I showed earlier does not do that. So this should have the proper gain as well, and it will, the DC, the voltage and the current in the DC pin here can be used to calculate the power added efficiency. So this potentially has wider applicability as a nonlinear model. It's not, wouldn't just be used for impedance matching network optimization. This shows the difference in, well, what I did was an oversweep of the load. The X's are the original measured data, and I did a sweep over a larger region of the Smith chart. And what this indicates is that the model degrades gradually. It doesn't just fall off a cliff. So I think this is, I mean, that's one of the limitations of a model, is that, you know, if we use this model, what happens if it sees an impedance over here? Well, we don't have any measured data over there, so it's not, probably it's not going to give real accurate results if you present that impedance to it. But if you're close enough to the region of the measured data, then the ANN model still produces reasonable results. Okay. I realize I'm out of time, but we are, Keysight and others are working together to do more with measured load pull data, more advanced optimization techniques, say using Smith tubes, where our test equipment people have wideband active load pull measurement systems. These are useful if you're needing to measure devices with wideband signals and determine what optimal impedances to present to those devices to get optimal performance. We can do a DPD simulation now and measurement and include load dependence. So we're working in a lot of areas in load pull. Yes?
One quick question on the nonlinear load pull modeling here. Is it in the plan where the E size also becomes an input for the model?
You mean in this model or?
No, in your future one.
I'm sorry.
Or maybe that's already like, I guess I'm just more looking at the enhanced modeling, like investigation, like so future is, from what you described, it sounded like it can generate a nonlinear model if there are phase and turning information provided.
Right.
And also sounds like if there are multi-frequency data, then the model is going to be able to predict over frequency.
Yes.
What about the device size? Like, for example, like a conventional scalable nonlinear model? Because a lot of times, actually, for mimic designers, like how to scale the device size is also like one of the variables for the PA design.
I think that could be included. Say if you've measured devices that are different sizes and you have that data, the ANN generator doesn't care. It's just another input variable. I think it could be included.
So users can actually customize the input features.
Yes. Yep. We have a number of different resources for people who want to explore this further. This is actually quite interesting. This is there are several videos from Matt Ozales on how to turn almost anything into a simulation model using ANN modeling. He does a really good job with this of showing what's possible. I mean, well, he has a simple test case, a simple example, but certainly creative people would be able to take this and create much more complicated examples, much more useful and interesting examples. But this is a really good tutorial, I think. So, and we have numerous examples on load pole measurements and simulations. Okay, thank you for your attention. Oh.